all want to live long and healthy lives. At a basic level, we need food, water and reliable sources of energy for transport and to keep us warm. In a modern dynamic society, people also expect to have a job, a healthy and clean environment to live in, and access to healthcare. Most of us would also like a comfortable home, as well as access to goods, services and technology. With the explosive growth in the world population, more and more people are demanding the lifestyle enjoyed by the developed world, and so the planet's finite supply of natural resources is under strain. Catalysts can provide solutions to many of the problems mankind faces in achieving these goals, and can help to make every precious atom count. Catalysis is a key technology in the chemical industry, which can significantly reduce the environmental impact of chemical processes and the energy required to carry them out. If catalysis is so important, then what is it and how does it work? A catalyst is a substance which is added to a chemical reaction, changing its course and affecting its outcome. What is really important about a catalyst is that it is unchanged at the end of the chemical reaction and can be reused millions and millions of times. It can increase the reaction rate, reduce the energy required for the reaction, and even determine what product is formed. Nature also uses catalysts to perform many processes that are essential for life, like breaking down food in your digestive system. Clearly, catalysis can play a crucial role in an era when it is important to conserve energy and reduce greenhouse gas emissions. It also plays a major part in improving the chemical industry, making it cleaner and greener, helping, for example, to eliminate toxic byproducts and reducing waste. Let's now look at a real catalyst in action. First, we're going to see how a catalyst can increase the rate of a reaction. The colourless liquid in this beaker is hydrogen peroxide and is actually reacting right now to form oxygen gas and water, but the reaction is too slow for us to see. Adding a small amount of catalyst can significantly speed up the reaction. In this case, our catalyst is an orange solution of iron nitrate, which we add to the hydrogen peroxide. After a short induction period, oxygen is generated much faster and energy is produced, which is indicated by the rapid fizzing and the quick rise in temperature. As you can see, once the reaction is complete, the solution returns to the original orange colour of the iron nitrate solution, showing that the catalyst is completely regenerated. The important concept when considering how a catalyst works is activation energy. For a reaction to take place, an energy hill needs to be overcome. The height of the hill is known as the activation energy. The higher the hill, the more energy is needed. When you add the catalyst, the activation energy is reduced, making the process more efficient. Scientists have developed very different ways to tackle the problem of how best to catalyze a reaction. The hydrogen peroxide experiment we saw earlier is an example of homogeneous catalysis. This means that both the reactant and catalyst are in the same state, a gas, liquid or solid. In this case, the hydrogen peroxide and iron nitrate solution are both liquids. However, it is also possible to use a solid catalyst with a liquid or gas reactant. We call this heterogeneous catalysis. We're now going to repeat our experiment, but this time we're using a solid catalyst, in this case copper. When you add the copper catalyst to the hydrogen peroxide solution, you can see the formation of bubbles of oxygen gas on the surface of the copper. This is where the reaction occurs. Another good example of heterogeneous catalysis is in the catalytic converter found in motor car exhaust systems. The catalytic converter itself is about 0.5 meter long, and its function is to reduce harmful emissions from entering the atmosphere. The catalyst is formed of nano-sized metal particles, coated onto the inside walls of a honeycomb-like ceramic structure. The channels inside the ceramic material are where the catalysis takes place. Molecules of, for example, carbon monoxide are able to enter the channels, where they are converted to the less harmful carbon dioxide, with the assistance of the catalyst. Most catalytic converters are also designed to convert nitrogen oxides to harmless nitrogen gas. Finally, these three-way catalytic converters convert unburnt hydrocarbons to water and carbon dioxide. We all want to reduce waste and use our precious resources more efficiently, and when we use catalysts to do this, we call it green catalysis. The production of nylon is a very large-scale process in industry. Nylon is the general name given to a family of man-made polymers, or plastics, called polyamides. And we use them in almost every aspect of our lives, from clothes to medical applications and household furnishings. One of the most commonly used polymers is nylon 6. The building block of nylon 6 is called caprolactam. The conventional uncatalyzed method to make these caprolactam building blocks produces a large amount of waste. 4 million tons of caprolactam are used each year just for nylon 6 production. But in the uncatalyzed process, for every 1 kilogram of the caprolactam produced, 4 kilograms of ammonium sulfate waste is also generated. This is not a sustainable process. Using a carefully designed heterogeneous catalyst, it is possible to produce the building block caprolactam from cyclohexanone using air and ammonia without producing any waste. The solid catalyst used here is a regular porous framework with catalytically active sites inside the channels through which the reactants pass. The channels have a diameter of about 0.7 nanometers. That is approximately 10,000 times narrower than a human hair. Isomers are compounds with the same chemical formula but a different structure. These are extremely important, especially in the pharmaceutical industry, where the biological activity of drug molecules is often very dependent upon the particular isomer. One well-known example is the drug thalidomide, which can exist in 2 isomeric forms that are mirror images or stereoisomers. Stereoisomers contain at least 1 carbon atom, having 4 different groups bonded to it, a chiral center. Each chiral center can exist in 2 possible arrangements that are mirror images. Following its discovery in the late 1950s, thalidomide was frequently prescribed to pregnant women to combat morning sickness. Tragically, it was later discovered that one of the stereoisomers was particularly harmful to the unborn fetus, whereas the other stereoisomer is an effective sedative. So this raises the very important question: can we use catalysis to control the course of a reaction such that only one of the possible stereoisomers is produced selectively? Well, this is a very tricky problem, but the answer is yes. Such a process is called enantioselective catalysis, or asymmetric catalysis. In the last example, we will look at the production of the compound menthol. In nature, menthol may be extracted from peppermint oil, but demand is high due to its wide usage in cough mixtures, cold remedies, toothpastes and sweets. With an estimated worldwide consumption of 6,000 tons per year, it is also produced in the laboratory on an industrial scale. There are actually 8 different stereoisomers of menthol possible, but using a special type of catalyst based on the metal rhodium, it is possible to produce it selectively as a single isomer, as we can see here. The homogeneous rhodium catalyst can be made in a single chiral form, and this is what determines the product isomer. We have shown that catalysis continues to be a key technology that is widely used across the chemical industry and plays a vital role in all of our everyday lives. In the examples we've looked at, we have seen how catalysts can speed up reactions, use less energy, produce less waste, and determine product selectivity. It is clear that catalysis can offer excellent control of reaction products, reducing the environmental impact and energy requirements. If science is to solve some of the challenges facing mankind in the years to come, it is clear that catalysis will have a big role to play.